Hello everyone watching this video, and today in this video we will discuss the moment of inertia for a rod. So to understand this, we have this rod. This is in the 3D, and we can assume that length of this rod is capital L and mass of this rod is capital M. And when we draw it, this will look like this in the 2D. This rod is in 3D, but here when we draw in the board, this in 2D this will look like this. So here in case of mass of this rod is capital M and length of this rod is capital L. So for this rod we take two axes, or we take two cases about which we will determine the moment of inertia. In case of in case of disc, or in case of a ring, we took four cases, but in the rod we have only two cases. In the first case, our axis of rotation is here, and the second case is axis of rotation is here. The first axis of rotation, this axis of rotation is perpendicular to this length of the rod and passing through its center, in which we take first case, the moment of inertia about an axis perpendicular to the length of the rod and passing through a center. And in the second case we take this axis. This axis is perpendicular to the length of the rod but passing through one edge. We can take this here also. So these here we have first case, and here we have second case, and two axes about which we will determine the moment of inertia for a rod. So we start here with the first case, in which we first draw a rod of length L and mass capital M, and we take or we will calculate the moment of inertia for a rod about an axis perpendicular to the length of the rod and passing through its center. So here its center, and this axis is perpendicular to its length and passing through its center. So about it we will determine the moment of inertia. So here we start the derivation of moment of inertia. For moment of inertia of rigid body, we have a formula I equals to integration dm r square. That means we need to take a small mass component dm at a distance small r. So in case of this rod, we take a small component here, and the length of this small component is dx, and the length of this small component from the axis is x. Axis is x. Okay. We have to determine the small mass of this small component dm. So we assume that the mass capital M is distributed over the length L, or we can say for length L, mass capital M is distributed. So for one unit length, mass is distributed M by L. So this is the linear mass density, or we can say mass per unit length. So this M by L is the linear mass density, or mass per unit length. So per unit length, or mass is M by L, but we need to determine mass for dx length. So for dx length, mass will be M by L into dx. For unit length, this mass is M by L. For dx length, this is M by L dx. So here we put the value I equals to integration dm is M by L dx, and the small r, the distance of the mass component from the axis, is x, and here the square. But before, we need here a limit also. So we put here, we take the mass component here, but we can take this mass component from here to here, anywhere on this rod. So length of here, the length of this end from this axis is minus L by 2, and length of this end from this axis is L by 2. So limit of integration will be minus L by 2 to L by 2. Next step, we take the constant out, then mass m and length is the constant, so we'll take out from the integration and we integrate x square with dx. But here we use one more property of integration. Here you can say that this limit of integration is minus L by 2 to L by 2, and in both of the cases this rod has the symmetry, so we can use this property. We multiply this integration with 2 and we integrate it from 0 to L by 2. Now we will solve it. I will be 2m by L, and integration of x square is x cube by 3 and limit is 0 to L by 2. Okay, in next step we put the limit to here m by L and we take 3 out. This is the constant. We put first upper limit at the place of x, that will be L by 2 cube minus, when we put the lower limit this will be 0 cube, and we solve it and we get that I will be 2 by 3 m by L, and this output of this will be L cube by, and the cube of 2 is 8. We solve it, we cancel out L with the square and 2 with 4. So output or moment of inertia about this axis will be I equals to 1 by 12 m L square. So this is the moment of inertia of the rod about an axis perpendicular to its length and passing through the center, which is I equals to 1 by 12 or 1 by 12th part of ml square. So this is the first case. In second case, we take the different axis which is passing through the one end here. I will be here. So in the second case, we take this axis to determine the moment of inertia. So we change it here, the case second, about an axis perpendicular to the length of the rod and passing through its one end, or you can say one corner also, end or corner. Okay. For the second case, we will not go through the same process that we used in the first case. In this case, we use the theorem of moment of inertia, and the moment of inertia, we know the moment of inertia about this axis, that I naught, which is 1 by 12 m L square. If the mass of rod is m and length of rod is L, then these two axes are parallel to each other and distance between two axes is L by 2. So we use here the parallel axis theorem, and according to parallel axis theorem, I equals to I naught plus md square. Here I naught, the axis about which we know the moment of inertia, mass is the mass of the body, rigid body, and the d, distance between two parallel axes. Then the I will be in the, we put the value here I naught is the our main axis about which moment of inertia is 1 by 12 m L square plus m, and the distance between two parallel axes is L by 2, and here square I will be 1 by 12 ml square plus ml square, and here the square of 2 is 4. When you add these two formulas, that will be when you can take ml square out and you can add 1 by 12 plus 1 by 4. So here I will be ml square and you can take LCM of 12 and 4. LCM of 12 and 4 is 12, and 12 are 1, and here 1, and 4 12 are 3, so this will be 3. So I will be ml square 4 by 12, and which will be, I will be 1 by 3 ml square. This is the moment of inertia for a rod about an axis perpendicular to the length and passing through one end or one corner. So the moment of inertia about this axis is 1 by 3 ml square, and moment of inertia about this axis is 1 by 12 ml square. So here we wind up over this video, today's video, and please make the notes and solve all the textbook examples and textbook questions from your book, and best of luck.